high-performance simulator. Qiskit is a tool used by tens of thousands of people globally who are all trying to build the future. Whether you're a researcher, developer, or just looking to get started, Qiskit has a number of features available for your needs, allowing anyone to do things like building your first quantum circuit, run cross-domain quantum algorithms, and study fundamental quantum phenomena. Maybe now is the perfect time to get involved yourself and find all the tools you need, including real quantum machines, an SDK through Qiskit, and a community that is happy to welcome you and answers any questions you may have along the way. You can get started today at Qiskit.org. And
Very good afternoon, ladies and gentlemen. I'm your host, Sarika again. Welcome back after what I hope was a refreshing lunch break. The energy in this room feels just as vibrant when you all actively participated in a series of excellent guest lectures. Now, as we transition to this promising afternoon workshop session, I invite each of you to bring your renewed enthusiasm and curiosity. The session promises to be highly enriching and edifying also. So let's make the most of this opportunity to learn, engage, and grow together. And for this excellent session, it's my privilege to introduce our esteemed resource person for today's workshop, Mr. Gnan Yalla. He's a distinguished AI and quantum computing researcher, currently serving as the Chief Technology Officer at datatech.ai. He brings over 5 years of hands on experience in building scalable SaaS products, leading AI innovation, and developing novel quantum algorithms tailored for real world applications. Mr. Yalla holds expertise at the intersection of quantum mechanics, quantum machine learning, quantum optimization, and hybrid quantum classical algorithms, making significant research contributions in areas such as quantum optimization, financial portfolio optimization, quantum memory stability, and secure satellite communications. His ongoing projects focus on quantum generative transformers, resilient quantum memory, and advanced quantum error correction circuits. As an architect and developer, Mr. Yalla has built AI powered adaptive learning ecosystems and domain specific AI agents for industries including healthcare, finance, legal, and edtech. He is highly skilled in deploying generative AI models for personalized learning and enterprise automation, as well as orchestrating cloud deployments across multiple platforms. Beyond his technical and research excellence, Mr. Yalla is a dedicated mentor and educator. He has guided over 15,000 students and professionals in AI, machine learning, data science, and quantum computing, both as a mentor and also as a trainer. He has been an invited speaker and representative at national and international workshops on quantum technologies, generative AI, and agentic AI, contributing to the global dialogue on the future of intelligent systems. Driven by vision to bridge the gap between theory and application, Mr. Yalla is committed to making quality education accessible to all and redefining the frontiers of learning, automation, and intelligent software. So please join me in welcoming Mr. Gnan Yalla to our workshop onto the dais with a big round of applause. I'm sure this is going to be such an edifying session, everybody. So over to you, sir.
Okay. Hello. Hello, everyone. I guess I'm audible, right? Is my voice audible to everyone here? Okay. Okay. So, yeah, cool. Thank you. Okay. Um, I was just getting some insights on how to use these new devices, so I hope you don't mind about it. First of all, a very good afternoon to everyone. Hope you guys had a very great lunch, right? Yes or no? Noah. Yarra. Okay, if you say no, you are a person like me actually. So completely all right. Okay. So first of all, why are we actually here? Leaving all your classes, all your stuff. Why did you come here? Because okay, completely all right. So first of all, thank you. Okay. So first of all, we are here for just one main reason. That reason is to know something about quantum computing. But before saying about quantum computing, I would like to explain very clearly about something called as quantum physics. So how many are you are from the physics background or like, um, some CSE background maybe? CSE, ra? Ah, okay. Nice. Now, what is a computer? Chala, వద్దు. Not a problem. But thank you so much. I actually got the insights from you. First of all, so before actually going into something called as quantum computing, let's actually see what is computer first of all. Now, okay. So a very great suggestion to everyone. You can consider it as an advice or a warning or whatever. My handwriting is very lame. So please try to hear me, okay, rather than following my handwriting. That's more better. మీకోసం నేను చెప్తున్నా. Okay, I'm telling it for your use case. Now, coming to what is a computer? So computer, I can simply say like I can directly say like it is nothing but a device which works from input to output. Yes, simple processing. A calculator. Calculator works with a particular input and a particular output. A simple device operation, simple stuff. We don't need to think that much about it. CPUs, RAM, we don't need to think that much about it. Simply to put, a single device, if we give a particular input, it gives a particular output. End of discussion. Now, our main goal is to know the core behind it. How? Can anyone say that? How you are getting a particular output if you're having an input? When you give a particular input, how your program or how your computer knows that it should give that particular output for that input. This is not only about question and answering. If I press F in my keypad or my keyboard, it shows F on my device. How and why? Okay, no need of how, just tell me why. ఎందుకు? Okay, now one more question. Computer is there, right? What is the subject which is responsible for creation of a computer? A computer create అయింది. We created a particular computer. People created computers, right? And computer gives a particular output for a given input, right? What is the entire logic behind it? How a particular computer gives an output for a given input? A subject in. I asked you how, you did not answer completely all right. What is the subject which wants to give you the output for a given input? Not computers. Don't be smart. There are two main subjects which are the core of a computer. First thing is something known as Boolean algebra. And the second thing is my favorite, physics. So these two are the primary reasons for a computer giving a particular output for a given input. A computer work avvadaniki. The main reason for the working of a computer comes from these two subjects. One thing is a Boolean algebra and second thing is physics. Why Boolean algebra? We will come to that. No worries. Why physics? The memory which you are using, the what can I say, the changes which is happening for a particular computer works on the concepts of physics. Why? Because, for example, if I press a particular button, or let us consider your phone is there. You guys are having touchscreen phones, right? How a particular touch of yours is reflecting on the phone? Can anyone answer that one? The people who are of, electrical departments or anything. So I have met a lot of people who are in ECA departments from this college. Can you answer that particular query? Smartphone work avadaaniki కారణం ఏంటి? If you touch a particular thing, how is that touch reflecting on the monitor, on the screen? How is that touch reflecting on the screen? What is the primary reason behind it? ECE people. It has nothing to do with physics as well. It's a computer. It's normal electronics and electronics physics, but still, ECE people. Can you answer about it? Kinda. Correct. Simply to put. So when you're giving a particular touch, simply to put, I don't want to use the exact words or exact stuff. Simply to put, a straightforward thingy. So when you're touching the screen of a smartphone or something, electric pulses will be, what can I say, detected. And normally, this is a smartphone screen. Normally, let us consider. So there is a fluctuating field here completely. Okay. And when you're touching a screen, like for example, you pointer touches on, so there will be a different type of fluctuation in this particular area. And based on that fluctuation, your smartphone will identify like, okay, there is something which happened in this particular place, and that is a touch unchip. Okay. So that is a core behind working of any touch screen. That is a core of behind working of any touch. Similarly, any kind of computation, this is just one of the example, but any type of computation or any type of operation, it works only with the underlying logic of physics, and the actual value which you are getting will work by the knowledge of Boolean algebra. So that's why what I like the most is are these two subjects, because they're the core of everything. Now let us go to why quantum and stuff. When I mention about physics inside a computer, what is this physics relates to? First thing, which we already seen, electro, meaning electrical, electromagnetic, whatever, just bring all the electrons in there. Second thing is thermal. So it deals with electro things as well as it deals with thermal things. Now, when you take these two operations, technically, in a very deep way, if you take these two operations, they come under your Newtonian physics. Or I can also say it like a classical physics. What is classical physics? Classical physics ante enti, simply to put. Can you say that? What is classical physics? What is Newtonian physics? We can call it as Einsteinian as well, not a problem. So Newtonian or Einsteinian physics. What is it exactly? As a classical physics ain't. So can I get one another or two another mics actually, because I will ask a lot of questions, so we can just pass through that. Okay, first thing, what is classical physics? As a classical physics ante ఏంటి? Okay, manual physics is the answer I got. Okay, manual. Technically or theoretically, kinda right. What exactly is meant by manual?
Macro physics.
Okay, macro. Sorry, bro. Yes, that's correct actually. That's the correct example. It's not manual, it's macro physics. So classical physics is nothing but macro physics, meaning a very clear example or very clear thing which I can directly say is that the physics being followed or applied, or I can go like followed by macro particles. Simply to put, the macro particles, I can call it as macro particles. Okay. Okay. So the physics which is applied to. Okay. So the physics which is being applied or which is followed by macro particles, meaning macro objects. Simply to put, the objects which you are able to see is called classical physics, or I can call it as Newtonian physics as well. Okay. That's a very simple and very straightforward definition of what is classical physics. For example, if I simply this a kerchief, right? If I drop it, what will happen? If I just leave it off right now, what will happen? It will it will fly, right? It will fall. Why? Because of gravity. So meaning, can I see this object? I am able to see it. Okay, and I am able to feel this object. I am able to touch this object. Meaning this comes under something known as macro particle. And the physics which is followed by a macro particle is called as Newtonian physics, or I can simply call it as classical physics, a straightforward example. Now, first, let's go clearly about what is this macro physics, and then we can move on to why we actually require the quantum. Now, when I said the two subjects which are heavily responsible for computers, I mentioned two things. What are they? Physics and Boolean algebra. What is the meaning of Boolean? What is Boolean? Enkide, everyone, like computers, electricals, chemistry, farmers, whatever, everyone should be answering this. What is Boolean? True or false? I can simply call it as binary. Binary can be one word, and true or false can be one another word. Zero or one can be one another word. I can have a lot of words here. Okay. Your classical physics or the core of your classical physics completely relies on this one thing. If you know or if you don't know, this is the truth. The complete classical physics relies on the Boolean algebra only. We will call it as deterministic value. I forgot the spelling, don't worry. Deterministic values. Meaning, I can calculate the particular projection or the particular travel or whatever with a particular formulas or with a particular properties. Meaning, when I throw this pen, for example, let us consider I'm throwing this pen at a particular velocity. Can I say where this pen is going to land? Yes or no? Straightforward answer. Yes, I can say it. Okay. And when I drop this particular kerchief without any force, can I say at what time, after how many seconds will this fall down? Can I or can I not? I can say that. Why am I able to say that? Why? Because this follows something known as this guy. And this guy, I mean, this is the like the core layer, which we don't actually see about, but is the reality. The reality of the core layer is a Boolean. And on top, if you go on, you will be having the deterministic values. This is determined by Newton, actually. He is the one who termed like by using physics, I can find everything. I can find the present, I can find the past, I can find the future as well. So that is defined by Newton. Why? Because it follows macro physics, kabatti, Boolean algebra, simply close. Now, so 0, 1. Now let's go back to computers. What is the basic unit of computer? What is the basic unit of computer? Computer it will not work if it doesn't have that particular thing. What is that? CPU లేని కంప్యూటర్ చూపిస్తా బెట్టా రియల్ I can show actually. Bits, exactly. Bits. Because you guys say CPU. Why? Because you guys think that CPU is the brain of the computer. I will give you entire IQ. I won't give you any data. Will you be able to answer any question? I will ask the question once again. I'll give you total IQ. Okay, I'll give you literal legit high IQ, like 200 plus IQ. I will give you, but I won't give you any data. I won't give anything. I don't even tell you what is your name. I don't tell you anything. I don't tell you English alphabet also. Is that IQ needed at that point of time? You don't know anything, dude. You don't even know to walk. What will you do with that IQ? Right? Now, you don't have that much IQ, but at least you have some knowledge, some koncham edo koddo goppo edo undi. And you have data. You are able to do some stuff better than the person who don't have data and who have high IQ. Yes or no? How many of you can accept this bullish statement? What I told, right? Why do you accept? Why? Because it makes sense, huh? Fine, whatever. So that is the entire deal. So the core of a computer is not CPU. CPU can be termed as a brain of the computer. True, I believe, yes. But the real reason why your computer works and why your computer is so powerful at this point of time is only because of one thing. And that one thing is known as bits. What are bits? Simply to put, I can say memory carrying memory or unit. Sorry, charge. Or anything, whatever you want to mention, like memory, you charge, data, whatever you can say, not a problem. Carrying unit. That is my bit. Okay, what is a bit? Simply to put, the information carrier, the basic information carrier of my computer is called as a bit. Okay, a very basic information carrier. If you are not having bit, light, computer koni waste. Pardon, but really. So that is a bit. The entire reason for the existence of computer, entire reasons for the smartness, everything is bit. Okay. And we will simply call it as classical bits and anochu, లేదా bits and anochu. That's always completely up to us. Okay. Now, I also mentioned previously, I previously mentioned that it works because of Boolean algebra, right? Thereby, your bits can only have the values of 0 or write this or in capital letters if you want, very important, 1. That's it. Okay. If you are asking, like if you are asked a true or false question, you will give either true or false. You can't give both of them, right? Unless you are so smart, you can't give both of them to confuse the teacher itself, right? Like this, huh? It will be true or false. Superposition of true or false. We will come to it actually. But when you are asked a particular true or false query, you'll only do either false or true. Okay. When you're switching on, when you're what can I say? When you're clicking a particular switch or particular something, you can either on the switch or you can off the switch. Yes or no? Fan on the. I can either switch on the fan or I can switch off the fan. I can't do both of them at the same time. Yes or no? Can I do both of them at the same time? Can I keep the switch in the middle position like this? Well, I can keep if the spring is very loose, but it doesn't do anything. It won't change or it won't affect anything. So that's the entire deal behind. On or off. Yes or no. 0 or 1. That is my classical bits and that is my bits and that's how my bits work. Binary data, binary carrying information. Ante, game lit. Now, let us consider you're totally having 1 bit. 1 bit on. What are the possible outputs? Correct. 0 or 1. I can either have 0 or I can have 1. Cool. Completely all right. I have 2 bits. What are the possible outputs? 4 values. What are they? 0, 0, 0, 1, 1, 0, 1, 1. I have 3. 8 outputs. Nakanత ఓపిక లేదు, so I won't write. But totally you will be having 8 outputs. Okay? Let us consider there's a basic thing. You will be having 8 outputs. Now, these are known as possible states. Okay? So if I have a single bit, the possible outputs can be 0 or 1. If I have 2 bits, the possible outputs can be any one of these 4 things. And if 4 low, any one of the guy is my output. Okay. Similarly, if I'm having 3 bits, out of these 8 states, so we will call it as a sample space. Out of these 8 positions or 8 outputs, any one of the guy is my actual output. Okay. Now let us consider you are having 1024 bits and you want to find the single best solution. Now, how many elements your sample space has? Okay, coming back, what is the sample space ante? Simply to put, for example, 1 bit is there. What are the possible outputs? 0 or 1. So, I can write it like this. Okay, na? I will call this guy as sample space. Now, if I go with 2 qubits, I can write my sample space as 0, 0, 0, 1, 1, 0, and 1, 1. Okay. So this is sample space, simply to put. And any one of the answer from your sample space is your original answer. Okay. These are nothing but the possible number of solution, the possibilities. These are all the possibilities. Dantlo any one of the guy is my actual answer. My actual answer is only one guy from that entire sample set. Now, when I go for 1024 bits, how many values will be there in my sample set? 2 to the power of 1024 samples. Now, I want to find the, what can I say, best answer among this 2 to the power of 1024. What I will be doing? For example, let us go back to 2 qubit state. 0, 0, 0, 1, 1, 0, 1, 1. The answer is 1, 1. Let us consider the best answer is 1, 1. How I can find 1, 1 is my best answer? Simply to put, brute force, the basic one. First, I will check with 0, 0. If it is yes, cool, lighter, no. Then I will go to this. No, no, yes, I got my answer. So this is how we can check. Now, let us consider 2 to the power of 1024 Annankara. Your answer is in 2 to the power of 1024 minus 2th state. Now, what you will be doing? You should be going all the way from 1 first position nunchi and to this position you should traverse it, yes or no? So on up to this particular position. Are you getting the point? Now, simply to put, consider it like a train. So these are the cars, and this is where the thing which you're searching for lies. Now, if the train only consists of 4 cars, first I will check this car, and then I will go here, and I go here, and then I go here, and I find the answer. Okay. Now let us consider your train has something like 50 cars. Cars ante nothing but bogies. Okay. 50 cars on the and the thing which you actually wanna find is in the 50th car. You can't go directly to 50. Again, I will go and check from the first car, second car, third car, and so on up to 50th car, and there I will find like, bro, this is where my answer resides and chip. So totally how many times I'm doing this checking operation? 50 times I'm doing this checking operation in order to get the answer. Okay. Now consider you are having 2 to the power of 1024 cars. Then how many times you should check in order to get your answer? If your answer is in 2 to the power of 1024 minus 2th state. So if your answer is in this particular state, how many iterations you should go? A lot. I don't want any mathematical value. Not simply to put a lot. Let us consider 2 to the power of 2048. Then, because it's infinite, okay, not like infinite, there's obviously a limit, but technically infinite. I can consider technically very large. Now, if I have technically very large number of bits, then if the possible solution is in my last state, then how many iterations it should take in order to actually go to that state? Definitely a very high number of iterations. And that's where my Moore's law comes into play. M-O-O-R-E. This guy says that, simply to put, this particular person says that the number of transistors doubles every year, every 2 years. Okay. So when I say the number of transistors doubles every 2 years, I'm simply saying him that this particular thing will increase. That's a basic thing what I'm trying to tell. Okay. When I say the number of transistors doubles every 2 years, I'm simply saying like this particular ante, the number of bits I'll be having will keep on increasing. And this will increase something called as an exponential way. Okay. And this will be keep on increasing in an exponential way up to certain state or up to certain limit where this particular method which I used will not be efficient. Because I said 5. It was cool. Bro, I got the answer. I said 50. Okay, kinda okay, but still I was able to get the answer. But when I said 2 to the power of 1024, it's too high. And when I said 2 to the power of 2048, it's very high. Now I can even go even more according to Moore's law, because the transistors will keep on increasing, and as the transistors keeps on increasing, what will happen? The bits which I'll be using for computation will also be increased. Simply to put, consider like the transistors are nothing but the units or devices by which you can do certain computation. Okay. So when I say the transistors keep on increasing, nothing but simply to put the data which I require for actual calculation will be increased. And as the data which I require for actual calculation increases, then what will happen? This particular method which I'm using in order to find the best answer will be not efficient. Are you guys getting the point? ట్రాన్సిస్టర్స్ ఇంక్రీస్ అవుతాయి, డేటా ఇంక్రీస్ అవుతారు. డేటా ఇంక్రీస్ అయింది అనుకోండి, బెస్ట్ సొల్యూషన్ కనిపెట్టడానికి యూజ్ చేసే మెథడ్ ఎఫిషియంట్ ఉండదు. సో వాట్ యూ మీన్ బై ఎఫిషియంట్? సింప్లీ టు పుట్, బెస్ట్. చాలు. డోంట్ గో లైక్ వర్క్ బై టైమ్. ఎఫిషియన్సీ మీన్స్ బెస్ట్. బెస్ట్ ఉండదు. Okay, it's not a good way, simply to put. Now, for that reason, now we have something known as quantum. So this is the actual problem which is being carried out. Ante enti, my data is increasing. So when my data increases, the possible solutions will increase. And as the possible solutions increases, I don't know where I can actually find my original data, or I can say like the best data which I actually require. Now, for example, let us consider a book. Okay, a book lo 5 pages are online. I am telling you to find an answer. It is easy. Okay, you can just turn out these 5 pages, you can get an answer. Now, if I give you 5,000 pages book and I told you to find the answer for one question, how will it be? It is a tough process, because you need to just keep on revising each and every page until you get a text which matches your question. And adi me answer outar. Same thing goes for computers also. When the data is low, the possible solution will be the same possible solution untadi. But when the data is low, what will happen is that I can find the best answer easily by using by taking minimum iterations. But when my data becomes high, when my data becomes too high, then what will happen? The possible solution will be there only, but the steps which I take in order to find that possible solution will be way more complex, and simply to put, way more inefficient in nature. And that is where your quantum comes into play. So why quantum comes into play? Simple. Now, what is quantum? Now let's go to the question, what is quantum? Let's leave this topic here. classical computing lo problem ఏంటని తెలిసిందా? Did you guys get what is the actual problem in classical computing? అసలు యాక్చువల్ గా ప్రాబ్లం ఏంటి? The problem which we are actually facing in classical computing is simply to put the way to find the best answer. Okay, and the way to find the best answer becomes complex because of Moore's law. Because number of transistors will be increasing, and as the number of transistors increase, what will happen? Data will increase, and as the data increases, I can't find my best answer efficiently. That is a simple deal which you need to remember. Now, come back here. Come back. Let me leave this topic there. Let's go back to quantum. What is quantum? Basic question. What is quantum? Microparticles. Yes. The quantum meaning ఏంటంటే very small. Did you ever hear the word called quantized? So quantized particle అంటారు, లేదంటే it is quantized అని అంటారు. So why quantized? What is this quantum? అంటే quantum కి meaning means very small, simply to put. And what is called quantum physics? The physics which is being followed by very small particles. The physics which is being followed by very small particles is called as quantum physics. That's a very simple definition. The very simple definition is that one. Okay. And why it is different? Ante it is different kabatti technically, really. Okay. So simply to put, classical physics works with the laws of Newton and Einstein. So actually Einstein's thing and Newton's thing both are technically same, but Einstein's thing is way more quantized than Newton, technically to speak. So okay, simply to put, what did Newton do? Newton discovered gravity. Okay, so simply to put, Newton discovered more than gravity. He literally defined how the planets revolve around the earth, but he was revolve around the sun. My bad. How the planets revolve around the sun because of the one principle of Higgs. But he failed to do one thing. What is that one thing? The people who are in physics enthusiasts and the physics guys, they might be knowing it. No one knows. Newton's equations does not follow the orientation of one thing. What is that? Okay, that's completely out of the thing. That's not what I was talking about. Okay, did you actually hear the Mercury's orbit? So okay, planets revolve around the sun by following the principles of Newton. Yes or no? Yes. Do you? Okay, I don't want to derive the entire formulas for that thing because it's quantum computing, not astronomic. But that's the entire deal. Like for example, a particular planet is there and the planet is revolving around the sun. It follows the rules of Newton actually. And the centrifugal, centripetal, and the force along with the gravity and everything. Okay, I don't want to talk about all those things. But the Newton's equations did not solve one thing. That is the revolution of this Mercury planet. It's all about everything. Any planets are satisfying. Mercury's one did not satisfy by something like 2.18 days, I guess. I don't remember actually. I did not revise this and all. But something like that. A miniature change ఏదో ఉండింది. So Newton's equations were not directly applicable for the revolutionary behavior of Mercury. So that's where your Einstein's theory of relativity came into play. And Einstein's theory of relativity actually solved this thing. Okay. So that's why if you take Einstein's equations and if you keep the light value, that is you'll be having a value called C in theory of relativity. Like prati values ki unta T equal to, you'll be having T by so there will be a formula and 1 minus V by C square and shit. So actually we don't need actual talk about that. But if you take that particular formula and if you substitute the velocity of actual light and actual V which we're actually seeing in the real world, it will be nothing being Newtonian equations only. But that works. So that's the theories which are classical. Okay, these theories gives rise to classical physics and that's why Boolean. But when you come to quantum, the Einsteinian and Newtonian which we have talked about will not work in quantum. Yes, technically to speak, they behave completely different from the actual theories of Einstein and Newton in my quantum. Okay, how? We will see that how and all very clearly, but there's a basic deal. The classical will not be applied in quantum. Why? Because the behavior of the subatomic particles, meaning the behavior of the quantum particles, is completely different from the behavior of these macroscopic particles. Macroscopic in the sense, simply to put, classical particles. How? See, for example, if you consider a man, okay, he is existing at a position X in this universe. Can the same man at a time t, can a same man exist at position Y at t? Yes or no? For example, let us consider you are here listening to me. Okay, at the same time, can you be in your classroom studying physics or studying whatever stuff? Can you be? Yes or no? We cannot. Okay, I am not talking about this physically present, mentally absent concept. I am talking about physical only, not mental. I don't care about mental. I'm just talking about physical only. So if you are physically present at a position X at a time t, you cannot be present at position at the same time t, right? So if you are here at this point of time, you can't be somewhere at the same point of time, right? But in quantum, the particles can be. Okay. For example, let us consider a subatomic particle. Name any one subatomic particle. Electrons. Okay, let us consider electrons. Okay. Electrons. Let us. Okay. First of all, electrons are not particles. So, but I'm just not considering that fact for this definition. Okay. But electrons are not particles. Okay. Okay. They follow something known as wave particle duality, which I will explain later. But that's the deal. Electrons are there. If electrons exist at position X at time t, they can also exist at position Y at the same time t. Okay. So meaning the same electron, only different electron got. The same electron can exist in more than one place at a point of time. So that is one of the law of quantum physics. So I will explain about it in a very clear way later. But it is the entire deal about quantum. Meaning the entire physics of quantum is completely different from the physics of your classical. That's a basic thing which you need to remember. Now, how this helps? Let us go to this particular example. This thing is there, right? Where a particular entity can exist in more than one position at a point of time. This particular concept is called superposition. This particular concept of your quantum is called as superposition. So what do you mean by superposition? Very simply to put, very straightforward, very easy, very simply to put, a particular particle or an entity can exist in more than so a particular position, or I can simply call it like where was I? Yeah, if a particular particle or a particular entity or whatever, if it exists in more than one position at the same time, we will call that concept as superposition. Just simply consider it like this. Mathematics and the mathematics keltam mellaga, but for now just consider it as the theory behind it. Okay, meaning, for example, if I take any particular particle called A, okay, this particle called A can exist at position called X at time t. At time t, I'm talking about all are at time t. And the same particle A can also exist in one more position called Y at the same time t. అంటే ఒకే టైంలో ఆ పార్టికల్ మోర్ దాన్ వన్ పొజిషన్ లో ఉండొచ్చు అనమాట. ఓకే, దట్ ఈస్ నోన్ యాజ్ సూపర్ పొజిషన్ సింప్లీ టు పుట్. నౌ the main deal why this quantum physics and quantum computing came into play and because of this one concept, and then entanglement ayane tarvata vachinayi. But the first main thing why your quantum computing came is because of superposition only. First thing is superposition only. Why? Because this guy solves the problem which we have defined before. Before I told you to stop at a particular point, right? What is that particular point where I told you to stop? What is that particular point where I actually told you to stop? అంటే నాకు ఎగ్జాక్ట్ గా చెప్పాల్సిన అవసరం లేదు. At least give me a theory. What is it exactly? Where the classical system fails, simply to put. Where it actually fails? When the data is more and the same concept again and again. When the data is more, the possible state can be there somewhere, and the steps which I take in order to find that possible state will be complex. That's a simple deal. Okay, why? Because by using classical physics, which is nothing but Boolean algebra, I can only check one at a time. I can only check one at a time. ఎందుకంటే నాకు either 0 ఉంటుంది లేదా 1 ఉంటుంది. I can't have both of them. Now, what is the superposition states? What does superposition states? Simply to put, a particle can exist in more than one position at the same time. Now, if I apply the same logic into the problem, let us consider n equal to 3. Anukundam. Okay. When I say n equal to 3, the total number of possible outputs are 2 cube. 8 possible outputs. Now, when I say classical, like let us consider A1, A2, so on up to A8. Okay. When I say classical, the entire deal is what? First check A1 and then check A2 and check the stuff until you get the desired state. Let us consider A8 is the answer. A8 answer anukundam. So first it will check A1 and then it will check A2 and then A3 and so on up to A8. Why? Why? Because when I talked about classical, I mentioned one thing. It is Boolean, meaning it can only do one step at a point of time. ఒక పాయింట్ ఆఫ్ టైంలో ఓన్లీ ఒక స్టెప్ నే తీసుకోగలుగుతారు, రైట్? సో దట్స్ వై వన్ స్టెప్ లైట్, సెకండ్ స్టెప్, థర్డ్ స్టెప్ అట్లా వెళ్తారు అనమాట. నౌ వాట్ ఈస్ ది సూపర్పోజిషన్ స్టేట్స్? Superposition states that I can have more than one at a point of time. Now simply try to apply the logic here. Now what will happen? Simply to put, instead of checking one by one, what will your quantum computer will be able to do ante, it will simply check the entire set at the same iteration. అంటే నేను ఓన్లీ A1 చెక్ చేసే టైం ఉంది చూసారా, ఆ ఒకే టైంలోనే మొత్తం చెక్ చేస్తారు అనమాట. ఓకే, and what will happen? Obviously, when I'm checking everything at the same time, I get to know that it is the answer, right? Let us go back to the train example. So I can say superposition as not going inside a car and checking and coming out. Instead, I will just keep a huge binocular and then I will check the train from far. And I will be like, bro, I can see my gold coin in that 50th car, bro. And shift. Okay, that is superposition, meaning when I see the train from far by using a binocular, I can see all the cars at the same time, right? Instead of going and checking each car one by one, I can check all the cars at a same time by using binocular. That's the simple logic behind superposition, meaning I can check everything at a same point of time. Okay, time at a single instance of time, I can check all the possible solutions. Got it? That is the basic principle behind your superposition. Okay, understood why quantum is better than classical at this point of time? Okay, so let us take something like 5 to 10 minutes of break and then we can start again. Okay, we can go to the next principle of quantum. Thank you.
All of you, all of you can go for. Take a short break and be right back in 10 to 15 minutes. Let's restart fresh energy again.
Hi, and welcome to 1 Minute Qiskit. This week, the question is, what is 1 Minute Qiskit? That's a great question. 1 Minute Qiskit is an ongoing series where I quickly answer frequently asked Qiskit-related questions, pulled from sources such as YouTube, Stack Exchange, and the Qiskit Slack. I'll also be sharing Qiskit tips and tricks along the way. I look forward to answering your questions. If you have a question you want answered, then please leave it in the comments. And if you found this video useful, you can subscribe for more 1 Minute Qiskit every Monday, as well as other quantum and Qiskit related videos. Thanks for watching and goodbye.
In quantum mechanics, a Hamiltonian is a mathematical description of the total energy of a system, incorporating both kinetic and potential energy. The system being described could be anything: a molecule, a single qubit, or a bouncy ball. A Hamiltonian can take different forms. It might incorporate different types of energy contributions, or be written in different coordinates or dimensions, which often makes them look very different. In quantum mechanics, knowing the Hamiltonian of your system is very important because it will allow you to solve the Schrödinger equation, the heart of quantum mechanics. The Schrödinger equation calculates how the system will evolve or change in time, which basically tells us everything useful we would want to know. That is why the first step of almost any problem or experiment boils down to calculating or identifying the Hamiltonian. In quantum mechanics, a Hamiltonian is a mathematical description of the total energy of a system, incorporating both kinetic and potential energy. The system being described
हेलो हेलो
So, what is the superposition in terms of physics? Clearly, okay, in terms of clear physics. Okay, so it's coming something like this, which, yeah, okay. Okay. Yes. So, Young's double slit experiment. Simply to put, so when I say superposition, the meaning of superposition is what? Something can be in more than one state. Okay, that's the real definition of superposition. Okay, so I mentioned a basic definition for the starters. So the thing which I said is a particle can be in position X as well as position Y at the same time T. So where this particle I call it as A and this also an A. So both are same particles. Can exist in more than one position at a time T. Okay. Now let's go to the real definition of superposition. You got this hypothetical definition, right? What is superposition and Cheppi? Okay, everyone got the hypothetical definition. Now let's go to the real definition of superposition. The real definition of superposition is when a single entity can exist in more than one state at a point of time. Simply to put, more than one state at time t. So this is the real example or real definition of superposition. And ఒక పార్టికల్ తీసుకున్నాం అనుకో, పార్టికల్ అనే కాదు, ఒక ఎంటిటీ, ఎనీ ఎంటిటీ ఇన్ ద సెన్స్ ఏదో ఒకటి, something, some whatever stuff it is. So an entity can exist in more than one state at a point of time. సో స్టేట్ అంటే ఏంటి? ఇప్పుడు మీరు ఐస్ క్యూబ్ తీసుకున్నా, ఐస్ క్యూబ్ వాటర్ లాగా ఐస్ క్యూబ్ లాగా ఉండగలుగుతా? Can the H2O atom or H2O molecule, sorry, can H2O molecule can be in a solid state as well as a liquid state at the same point of time? Same point of time. It cannot be. Okay, but if you take a quantum particle or if you take a subatomic particle, that can be there in more than one state at a point of time. That is the real meaning of superposition. Now, in order to say it in a very clear way, I can simply put like electron, the best example ever. Electron. So in order to explain the superposition of electron, we need to know something about YDSC, Young's double slit experiment. So that's where we actually go. Here. That's okay. Now, what did this young scientist did? And a young scientist card, what very young. Okay, so what is this young scientist did? And very simple. So he just made something like this. Okay, and here he had something called as a screen or whiteboard or blackboard, ఏదో ఒకటి మీ ఇష్టం, ఏదో ఒకటి పెట్టుకోండి, ప్రాబ్లమే లేదు. Screen. Now, first what he did is very simply he tried to shoot an electron beam. So నాకు గన్ను డ్రా చేయడం రాదు, but okay, nothing but he shot an electron beam. Okay, electron beam is nothing but a gun which shoots electron. Okay, just simply consider it like that. Okay, don't go to actual definitions. Electron beam, nothing but a gun which shoots electrons. Okay, saripin. Now, and then he observed something like this. Okay, so I'll just draw the screen. So when he did this, so when he was shooting the electrons, the screen looked something like this. So screen ni మనం front లో చూసినట్టు అనుకుందాం. So the screen looked something like this. Okay, meaning, a clear meaning is that this point is there, right? So the place where the slit is there. So ఈ hole ఉంది చూసారా, దీన్ని మనం slit అంటాం అన్నమాట. Okay, we'll call that hole as slit. Okay, when he made a single slit and shot the electron beam, then what happened? He saw this pattern. Perfect. Correct. Yenduku. So a hole is there, paintball. Let us consider paintball or you're painting. So when a hole is there and you're shooting from that hole, then obviously you're going to see a straight line. Okay. Common sense. Right now. So this was perfect. This was perfect. And from here, Young decided or Young said that electron is a particle. Obviously, if it is a particle, then only when he shoots from, it will just travel from that hole, and it will, what can I say, it will attack, or it will just place on the screen, thereby making this structure, a straight line structure. Cool. Done. Electron is a particle. He decided electron is a particle, bro. Very good. I'm so happy. Now he increased this split. Okay, single split ni కాస్త double split చేసాడు, and he shot the same electron beam. Same electron beam ni shoot చేసాడు. Okay, now what will happen? And same he kept a screen. Now smart గా ఆలోచించాలి, like తెలుగుగా ఆలోచిస్తే what will happen? This electron can either, if it is a particle, obviously electron is a particle based on a previous example, right? So if it is a particle, at a point of time it can travel either through this slit, else through this slit. Either or, either slit 1 నుంచి పాస్ అవుతారు ఎలక్ట్రాన్, లేదా స్లిట్ 2 నుంచి పాస్ అవుతారు, రైట్? సో అట్ పాయింట్ ఆఫ్ టైం నేను ఒక బుల్లెట్ వేసాను అంటే ఒక ఎలక్ట్రాన్ షూట్ చేసినప్పుడు ఇట్ కెన్ ఎయిదర్ గో ఫ్రమ్ 1 ఆర్ ఇట్ కెన్ గో ఫ్రమ్ 2. Okay, so what can be the final output be, or what can be the final screen be? How it might look like? ఒకవేళ ఇటు నుంచి వెళ్తే ఎలా వస్తుంది? ఇక్కడ స్టిక్ అవుతారు ఎలక్ట్రాన్స్. ఒకవేళ ఇలా వెళ్తే ఇలా స్టిక్ అవుతారు, రైట్? సో ద ఫైనల్ స్క్రీన్ మైట్ బి సంథింగ్ లైక్ దిస్. ఎస్ ఆర్ నో? అర్థమైందా పాయింట్? సో ఫర్ ఎగ్జాంపుల్ నేను ఒక హోల్ పెట్టినప్పుడు ఏమైంది? I just got a single line. I just got a straight line. Everything was perfect. Electron is a particle. Now if I make 2 holes, I should be getting 2 lines, right? Why? Because electron can either travel from slit 1 or it can travel from slit 2. I don't know. It can go from any slit at a point of time. Thereby I can get 2 straight lines, right? Agree or not agree? Agree everyone? So this is how it should be. Why? Because electron is a particle, but it can either go from go through slit 1, or else it might go through slit 2, and I will get 2 straight lines. But what happened is that when he performed this experiment, he got in the screen not these 2 lines, but he got something like this. So this is a dark line, very semi mild. So this is the pattern he got actually. So he did not get the 2 straight lines actually. Instead, he got something like this. How? Why? Because see simply, in a first experiment, it was proven that when I have a single slit and when I shot electrons through that single slit, I just got a straight line. Saying to me or expressing that electron acts like a, what can I say, that particle, and went through that straight hole and stuck on my screen. But when I had 2 slits, what happened? My electron, it should show this particular thing, but instead it showed something like this. Why? And that's where the actual doubt started, like how? And then he began to understand this pattern, and this pattern is something known as inference pattern. Meaning, very simply to put, let us consider, okay, let's just go back here. Now, this was the experiment, okay, where we considered the electrons as particles. Now consider electron as wave. So the pattern which he observed, which is known as inference pattern, can be achieved only if the particle is if the entity which is passing is a wave. So why? Because simple. See, let us consider it's a wave which is passing through here. So దీని నుంచి ఒక wave వస్తుంది అనుకుందాం. Like let us consider a wave is passing. Now what will happen if a wave passes? It goes like this. Okay, from slit 1, and from slit 2 as well, it goes like this. right? Yes or no? So water mere eppudaina raళ్ళు వేసారా in rivers or something? You saw that ripple pattern, right? So now if you see this pattern, this is what can I say? This is a wall, and this is how it looks like. And wherever, like for example, okay, this is a mathematical term again, but what will happen is the waves which are having or which are coherent to each other will add up, creating a heavy intensity. So that heavy intensity can be observed in the middle place. So this is high intensity or high coherent area. Okay, meaning the waves with the same amplitude is added so as to get a, what can I say, so as to get a stronger intensity or something like that. Thereby this will be bright, and if you just keep on going, it will be become lighter. Why? Because they will be having same amplitude in the opposite direction, thereby cancelling each other out and thereby creating an empty spaces. So here you can see empty spaces. So these empty spaces are formed because of decoherence. So what is this coherence and decoherence concept? It is a concept of waves, simply to put. So how it will happen? Very easy. Amplitude plus amplitude. Let us consider, I'm not making a clean sine of omega t formula or something. Direct basic example I'm giving. So this will give rise to big amplitude. Simply to put, okay, simply to put. And this concept is called coherence. Same phase, same angle adds up so as to get a heavier beam, or you can say high intense beam. Now, if I have the same amplitude, I mean the same phase or something in opposite direction, then what will happen? They will cancel each other out and thereby forming nothing. Okay, this concept is decoherence. So that's a simple thing of this YDSC experiment. YDS and a Young's double slit experiment, meaning the waves which are powerful, the waves which are of same amplitude and same phase will be added so as to get a higher one. So simply to put, coherence nature, thereby getting or thereby giving rise to my heavy interference pattern. దాని తర్వాత ఏమవుతుంది, like if you see this figure perfectly na, so you can see exactly. So where the waves are adding up, you will be having high intense period, and where there are gaps or where the waves are cutting off, you will be seeing spaces. That's a simple deal behind this YDSC. So what he tried to take out from this ante, that inference, okay, this inference pattern which he got can only be achieved by waves. But what he shot electrons. He did not shoot waves. He shot electrons. So in the first case, where we had where he has a single slit, electron acted like a particle. Okay, thereby forming him a straight line. So it was cool up to there, and he understood that electron is a particle. But when he has two slits, what happened? He got an inference pattern, thereby saying that electron is like a wave at this point of time. So this is a superposition. This is the exact meaning of superposition, meaning an electron can exist both as a particle as well as a wave. And we will also call it as something known as wave particle duality, which is created by a guy called as de Broglie. Okay, so he is the one who got to know this theorem, okay, which is known as wave particle duality, meaning an electron can exist or can behave both like a particle as well as a wave. So how he did this ante, so he gave rise to a very small formula which is known as lambda equal to h by p, which is equal to h by mv. So this clearly gives the direct relation between a wave and a particle. Why? Because momentum is a feature of particle and lambda is a feature of wave. He just made a direct relation between the particle and a wave, thereby giving rise to a wave particle duality. Okay, and this is the real meaning of superposition. An entity can exist in more than one state at a point of time. Okay, the real meaning is this one. Okay, so yeah, that's the deal. So this is how it actually looks like in subatomic world. So when I say superposition, it's not all at once. It is this concept which is giving rise to that all at once concept. Okay, so that's the basic deal behind it. Now, let us go to the superposition in quantum computing itself, not quantum physics, right? Well, okay, so before going here, okay. Now, I hope you guys have understood the superposition concept and everything, right? Now, let's go to the fundamentals of quantum mechanics, which is eventually equal to quantum computing. First thing which is there in a quantum computer or quantum, what can I say this as? Quantum mechanics is the concept of qubits. So, what are these qubits under? Qubits are nothing but quantum bits. I'll call it as quantum bits. Quantum bits are nothing but qubits. Okay. So, what are these qubits? Very simple. The basic unit of quantum is this qubits. Okay, that's a simple deal. And what did I say about the basic unit? The basic phenomenon of quantum is that it exists in more than one state. That's a basic deal behind it. Now, when I say classical bit, okay, so throughout quantum computing, na, what we'll be doing until we won't be saying bit and qubit. We'll be saying classical bit, which will be determined by CL bit. CL bit ke meaning a classical bit ani adham. Okay. Now, when you're dealing with a classical bit, it can either be 0 or 1, right? But when you're dealing with qubits, they can be 0, yes. They can be 1, yes. And they can be both 0 and 1 as well. Okay. This is a primary deal of superposition. This is the primary deal of superposition. It is okay. We should not look at it in a way like combination of states. No, that is not the correct word. You should not see in that way. Okay, don't get confused for combination of states. No, you should say it like existing in more than one state. That is the correct word to use. Do not go like superposition is combination of states. Do not go like that. It is not a combination of states. Combination of states ke meaning ఏంటంటే mixture లాగా అయిపోతుంది. It's not a mixture. Superposition state is not a mixture. It is nothing but more than one state at point of time. That's it. It's not combination. There's a huge difference between combination and more than one. Okay. Superposition meaning is more than one state. Okay, just simply consider like that. This is the real meaning of it. You should not, if anyone tells you like superposition is nothing but a combination of state, it's no. It's not a correct word to use. It is not a combination. Combination అంటే ఏంటి? రెండింటిని మిక్సీలో రుబ్బితే అది కాంబినేషన్ అవుతుంది. But it combination కాదు. It is nothing but all at once. That's it. Now let's go to some kind of mathematics. I hope everyone is having their books, right? Books, pens. Nice. Okay. Now, firstly, if you want to clearly understand quantum mechanics or quantum computing or quantum computing on it, so quantum computing, in order to do a particular thing, we'll build a quantum circuit first of all. మన క్యాషువల్ పైథాన్ లాగా సి లాగా డైరెక్ట్ గా కోడ్ రాసేస్తే ఏం వచ్చేది క్వాంటమ్ కంప్యూటర్ లో. సో యూ షుడ్ బిల్డ్ సంథింగ్ కాల్డ్ as a circuit, and after building a circuit, then you will run the circuit. So first step is to build a particular circuit, and if you want to build a particular circuit, you need to know how that works, right? And that works because of quantum mechanics, or based on the principles of quantum mechanics. Now how it actually goes under simple. First, quantum mechanics. first thing which you want to understand about quantum mechanics is this qubits. As I said, qubit is nothing but 0 or 1 or 0 and 1. Kada? I will represent qubit as psi. Okay. So what is the meaning behind this is called as state vector. Okay, please everyone copy and everyone make a note of it. Everyone get to know about it. It is very important. It is రాకపోతే quantum computing చేయలేరు. You can't do it. It is not like AI where you, even if you don't know the logic behind optimization, you can code. No, it's not like that. అలా చేయడానికి అవ్వదు quantum computing. So you need to know this, then only you can code this, else you can't code it. Okay. So first is qubit is represented by C. I call it as C. Some guys will call it as C. Some guys will call it as psi. I don't care. I call it as C. Okay. So which is represented as state vector. దీని మనం state vector అంటాం. So what is the state vector? This state vector is nothing but it represents the quantum state. Okay. So in classical physics, in bits, for bits we have a value 0, value 1, ante. But for qubits we have something called as state. For bits we have values, but for qubits we have states. So you define a qubit based on the state. Qubits do not have a value. Qubits ki values undavu. Qubits ki state untadi. Okay, that's the first thing which you need to remember. Why? Because it is a wave, not a particle. Okay, simply to put, it is a wave kind of thing. Just consider it like a wave. Consider it like a wave, not actually a wave, but it's completely something related to wave. Now, so how can I write this psi value as? I can write it in something like this. I will be writing it like alpha 0 plus beta 1. Okay, so this is the actual thing which I will be writing my psi as. So what is alpha? Alpha is the amplitude for state 0 and beta is the amplitude for state 1. Now to say it in a very clear way, if I square this alpha, okay, if I simply square this alpha, I will be getting something known as a probability of the state being equal to 0. Okay, alpha square is the probability of the state being equal to 0. Okay, why? Because this is there, right? This one. This is the superposition state of 0 and 1. Okay, this equation, this state vector defines the superposition state of 0 and 1. Typically, a classical bit called A, okay, can be 0 or it can be 1, but it can't be both of them at the same time. So in order to define both of the states at the same time, that is nothing but a superposition thing. So we write our qubit like this. Okay, we write our or we define our qubit in this particular way, called as psi equal to alpha 0 plus beta 1. Okay, superposition state of 0 and 1, simply to put, with alpha being the amplitude of state 0 and beta being the amplitude of state 1. And if I do alpha square, okay, then I will be getting the probability of the state being in 0. అంటే ఆ స్టేట్ 0కి దగ్గరకు వచ్చే probability అని చెప్తారు అనమాట. So how much probably it can be 0? What is the probability of that state being equal to 0? That is defined by alpha square. And beta square defines what? Probability of the state being 1. So why this thing? And very simple. So I have a superposition state, right? Now the point goes like this. When I'm actually measuring the value of the superposition state, ఈ సూపర్పోజిషన్ స్టేట్ ఒక వాల్యూ నా యాక్చువల్ వాల్యూ నాకు కావాలి. ఆ యాక్చువల్ వాల్యూని నేను మెజర్ చేసే టైంకి ఏమవుతుందంటే దిస్ విల్ డీకంపోజ్ ఆర్ ఐ కెన్ కాల్ ఇట్ యాజ్ డీకన్స్ట్రక్ట్ టు ఎనీ వన్ ఆఫ్ ద బేసిస్ స్టేట్. సో బేసిస్ స్టేట్ అంటే ఏంటి? 0 or 1. Meaning, very simply to say, or very easy, very direct way to understand is that, for example, let us consider I am having a superpositioned wave. నా దగ్గర ఒక superpositioned wave ఉంది లేదా ఒక superpositioned particle ఉంది. Okay. Now, if you actually wanna measure the value of the superposition particle, ఒక సూపర్పోజిషన్ పార్టికల్ ఒక వాల్యూని మీరు మెజర్ చేయాలనుకున్నప్పుడు ఏమవుతారంటే ద మూమెంట్ యు మెజర్ okay. So yeah, where was I? What was I saying at the end? Really, I forgot it. What was I saying at the end? Measuring a superposition. Yeah, okay, coming back. So, when we actually measure a superposition state, for example, let us consider I have a particle or I have something which is a superposition state. Okay, let us consider this pen is a superposition state. Okay, and when I actually want to find the value of the superposition state, okay, superposition state on a vector or wave or whatever stuff it is, if it is in a superposition state, and if I want to find the value of the superposition state, then the moment I measure it, so if I want to find a value, it's technically mean that I want to measure it off, right? So like if I want to find the amount of water inside this, what I should be doing, I can simply look at it and can simply say, let us consider I don't have sticker. Then I should be measuring it. Okay. So if I want to find the value of something, I should be measuring it. Similarly, let us consider I have a superposition state. and I want to find the value of the superposition state. But what will happen is that the moment, okay, the exact moment when I actually want to measure the superposition state, it will be decomposed into one of its base states. What is the base state? And a simple. Okay, fine. Okay, so you remember that 0 plus 1 thingy, right? Okay, ma, thank you. Yeah. So you remember this thing, right? This particular stuff. Now, these guys are known as my base states. Okay. So the moment when you actually measure a superposition state, it will decompose or it will deconstruct. Best word to use is decompose. It will decompose to any one of the base states. Any one of the base state ki decompose అవుతారు అన్నమాట. So technically you can't see a superposition state. ఒక superposition state ని మనం చూడలేము, కనిపెట్టలేము. You can't calculate or you can't measure a superposition state. Keep that in your mind. Okay. So this thing is known as Schrodinger cat experiment అంటారు దీన్నే. Experiment. So technically you can't see a superposition state. So Schrodinger's cat experiment goes like this. You have a cat inside a box. I can't draw cat, so that's why I'll draw a circle and I'll name it cat. Okay, consider. And you have something known as an electron gun, or not like an electron, I can simply be like a radioactive particle. వద్దులే. I don't want to say the real Schrodinger experiment. So for your clean reference, I can be like an electron gun. ఒక గన్ ఉంది అనుకుందాం. Don't be like radioactive. Real experiment goes like yes, an radioactive element with a half life అని చెప్పి ఉంటుంది. We don't need to care about that much. Just simply consider like a gun. You're having a gun. Okay. And this gun obviously has a bullet. So the thing goes like this. The Schrodinger's cat experiment goes in a very simple way is that this gun has a 50% probability of shooting. Okay. And 50% probability of not shooting. Okay. And this cat is inside a particular box. So a box lopali cat undi and a box lopali gun kuda undi annamata. So that gun has 50% probability of shooting and the remaining 50% probability of not shooting. Okay. And this cat is inside a box. Now, if I ask you a question like is cat alive or dead, what will be your answer? So that is Schrodinger's cat experiment, simply to put. Oka box undi. So inside a box, keep a cat and keep a dog. Sorry, my bad. Keep a gun as well. And that gun has 50% probability of shooting and the remaining 50% probability is not shooting. Okay. If first 50% probability is done, then it will shoot, the bullet will go, cat will be dead. Okay. And if it is the gun will not shoot, the cat will not be dead. The cat will be alive. I closed the box. I kept the box here. And if I ask you the question, whether the cat is alive or dead, what will be your answer? Let us consider the gun will not have sound because smart people will be like, I don't hear the sound. Okay, gun has silencer, bro. Okay, now say what is the answer? Is cat alive or dead? We can't say it technically. Like might shoot, might not shoot. We don't know, right? At that time, the answer goes like this: the cat is in a superposition state of alive and dead. Yes or no? So at that point of time, in your point of view, the cat is in a superposition state of being alive as well as dead. Meaning it can be there and it can be this as well. So two states occurring at the same point of time. Okay. So, but now you want to measure that value until you want to actually see whether it is alive or dead. You will open the box. You will get one thing. Yes or no? You will get either alive or dead. Gani, the moment when you open the box, it will not be a superposition. Yes or no? The moment you open the box, you will get the answer whether it is alive or dead. And meeku answer vachestadi when you open the box. So meaning when you measure the superposition state will decompose to any one of the base states. Understood the meaning behind it? There's a clean meaning behind it. Okay, so just keep a cat inside a box and keep it in with a gun which has 50% probability of shooting and 50% probability of not shooting. Then until you see inside a box, technically the cat is in a superposition state of being alive and dead. Why? Because we don't know how it is exactly. But the moment we open the box and we actually see it, it is either alive or dead. Either like it can be alive, else the gun is shot and it can be dead. So a superposition state, when you measure it, will decompose into one of the base state. Okay, and that's the reason you cannot find a value of a superposition state. Superposition state ఒక వాల్యూని మనం కనిపెట్టడానికి అవ్వదు. You cannot calculate a value of the superposition state. You can simply feel it. That's it. Understood the concept? Now that's where this guy comes into play. This one. So when you are trying to measure a superposition state, it will decompose to either 0 or 1. Right? Yes or no? Now you understood the concept? When you're measuring a superposition state, what will happen? It will either decompose to 0 or 1. Either 0 keltar లేదా 1 keltar. Now why I took the stress of explaining all this ante in order to explain alpha square. So what did I say about alpha square? The probability of getting 0. Meaning is that when I measure that superposition state, the probability of that superposition state when being measured gives the output as 0 is given by alpha square. Okay, and the probability of the output being 1 when I measure the superposition state is given by beta square. Got it? So simply to put, okay. So simply to put, you can go it in this way. Let us consider my state looks something like this, which is something like 0.2 0 plus let us consider this is the square, like 0.2 is nothing but alpha square, and beta is square. Okay, let us simply consider, else wait. Let us consider alpha square is 0.2 and beta square is 0.8. Let us simply consider it in this way. Then what will happen is, and let us consider I have a state of root 0.2 of alpha, sorry, 0 plus root 0.8 of 1. Okay, let us consider this is my state. Okay, so why? Because I mentioned you that psi looks something like this. Right? So there is a superposition state, this is a qubit. And let us consider this is the deal. Okay, psi equal to root 0.2 into, root 0.2 of 0 plus root 0.8 of 1, meaning alpha square is 0.2 and beta square is 0.8. The real meaning goes like this. So point ఏంటంటే ఇప్పుడు when I measure this superposition state, when I actually measure this superposition state, the output is 20% probability of being 0 and 80% probability of being 1. This is the meaning behind it. Got it? 20% అంటే ఏంటి? 0.2, 80 అంటే 0.8 మీకు ఆల్రెడీ తెలుసు. Thank you. Okay. So that is the entire meaning behind this alpha and beta values. Okay. So simply to put, they determine the amplitude of the wave. And one more, like in a simple manner, but regarding the quantum computing point of view, the square of those values, the square of the coefficient values gives you the probability of the outputs. Okay. So that is the real meaning behind it. Advainda, understood the superposition concept, understood the qubit equation. Okay, the superposition equation of qubit. Now let's go to even more mathematics, which is like the properties of quantum mechanics directly. Okay, the direct properties. So I heard that you guys are having a new subject called quantum mechanics, right? Quantum mechanics subject started in the kada. Yes, I just heard it. Okay, so it might be useful for that as well, and it's very good actually. So just try to keep that in your mind. First thing, which you want to remember is, or which you want to which you want to keep in your mind is, quantum states belongs to or exists in something known as Hilbert space. Okay, the first thing which you want to keep that in your mind, quantum states exist in something known as Hilbert space. So what is this Hilbert space? First thing we want to think again, Hilbert space means it's a complete space. So it's complete in nature. Inner product of vectors will be there. Vector norms, I can simply say. Okay, and simply to put, people call it as infinite dimensions, but technically it is not infinite dimensions. So real Hilbert space చూస్తే మీకు infinite dimensions might be there, but when you're dealing with a quantum related Hilbert space, you'll be having 2 to the power of n dimensions. Okay, so what is this n? N is the number of qubits. Okay, for a single qubit state, single qubit state ante enti? N equal to 1. Okay, for a single qubit state, the Hilbert space responsible looks something like this, c square. Okay, this is for a single qubit space. So for a single qubit space, we will define or we will determine Hilbert space as c square. Okay, so Hilbert space అన్న చాలా పెద్దది. ఓకే, ఆ Hilbert space లో ఈ c square అనే సబ్సెట్ లో, అంటే ఆ సబ్ స్పేస్ లో సింగిల్ క్యూబిట్ స్టేట్ ఎగ్జిస్ట్ అవుతారు అన్నమాట. Okay, that is the first thing which you want to keep it in your mind. Hilbert space is a space. Okay, it's a very big space. And when I talk about single qubit state, all the possibilities, meaning all the vectors and everything of the single qubit state exists in a subset of Hilbert space called as c square. Okay, and దీనికి మీనింగ్ ఏంటంటే రియల్లీ C2n. Okay, that is the real meaning behind it. And n equal to 1 కాబట్టి it is nothing but C2. But for example, let us consider 2 qubit state. So when I have 2 qubit state, what will happen is that my Hilbert space will be what? Power of, come on anyone. So I said this there, right? So H belongs to C of power of 2n, where n is what? Number of qubits. For 2 qubit state, it will be equal to 4. Okay, with a dimension of 2 to the power of 2. So totally it is of 4 dimensions. Okay, so that's a simple thing which you need to remember. So all these quantum operations will happen in Hilbert space, and a complete Hilbert space kuda kaadu. A Hilbert space of 2 to the power of n dimension which is a subset of a Hilbert space called as C to the power of 2 into n. N is the number of qubits. Simple and straightforward thing to remember. Now, what is meant by complete? So where did you see this word complete? Where did you see this word called complete? From where did this complete came into play? When I was explaining about Hilbert space, here I mentioned like complete. Okay, Hilbert space is complete in nature. So what is the meaning behind this complete ante? Very simple. In a complete thing, what will happen? I can call something as complete in nature when every Cauchy sequence, okay, will converge within the limits. This is the meaning of complete in nature. So when I say complete, as a complete ante enti, it with respect to geometry or spaces or something, simply be like every Cauchy sequence existing inside that space will converge within the limits. అంటే ఆ లిమిట్ దాటి బయటికి వెళ్ళలేరు, దానికి ముందే కన్వర్జ్ అయిపోతా అన్నమాట. Okay, when this thing happens, when this thing is satisfied, I will say it is complete in nature. What is a Cauchy sequence? Simple. So I will say Cauchy is satisfied. Cauchy ఇది. I will say Cauchy is satisfied for x of n basis state. Basis state అంటే nothing but an entity. Deep గా ఏం ఆలోచించొద్దు. When I say basis state, just consider it like an entity or axis అంటే చాలు, ఇంకేం అక్కర్లేదు. Okay, so a basis state x of n or xn, simply consider a basis state xn. For a basis state xn, there exists a value epsilon greater than 0. Okay, there exists a value, any value, మీ ఇష్టమైన లెటర్ అయినా పెట్టుకోండి, ప్రాబ్లం లేదు. ఎప్సిలాన్ గ్రేటర్ దాన్ 0 బియాండ్ n, అంటే n కన్నా పైన ఉంటది ఈ ఎప్సిలాన్ వాల్యూ. ఓకే, బియాండ్ n you have an epsilon value greater than 0 and for every small m and small n which is greater than n. Okay, for every small m and small n which is greater than n, all are random variables which I am taking. మీకు కావాల్సిన మీ ఇష్టమైన లెటర్స్ కూడా వాడుకోవచ్చు, ప్రాబ్లం ఏమీ లేదు. Okay, take a random variable m, small m comma small n which are greater than capital N. Then xm minus xn is always lower than epsilon. So if this condition is satisfied for every xn, ప్రతి x అనే బేసిస్ స్టేట్ కి, మీనింగ్ ప్రతి x అనే వెక్టార్ కి, వాట్ ఈస్ ఎ వెక్టార్? ఫర్ ఎగ్జాంపుల్ ఇఫ్ ఐ టేక్ a తీసుకున్నాను అనుకోండి, దీని వెక్టార్ ఎట్లా ఉంటుంది? a1 a2 so on up to am or an. So this is a vector. Okay, simply consider this is a vector. Okay, simply to put this is a vector. Okay, straightforward, ఇంకేం అవసరం లేదు ఎక్కువ, just this is a simple vector. Now when I say something is Cauchy in nature, Cauchy sequence అంటే ఏంటి? For every vector, okay, for every vector, if I take a value epsilon greater than 0, epsilon greater than 0 అని ఒక వాల్యూ తీసుకున్నా, n అనే వేరియబుల్ కి ఎక్కువ ఉంది అది, దాంట్లోనే నేను రెండు చిన్న వేరియబుల్స్ తీసుకున్నాను అనుకో, m and n, ఇది సాటిస్ఫై అవుతారు అనమాట. ఓకే, సో దట్ ఈస్ ద మీనింగ్ ఆఫ్ Cauchy సీక్వెన్స్. వెరీ స్ట్రైట్ ఫార్వర్డ్. గ్రాఫికల్ వేలో చూడాలంటే సింప్లీ టు పుట్ just consider it like this. Epsilon greater than 0, just take a random epsilon value. ఇక్కడ ఉంది అనుకుందాం, this is epsilon. Okay, beyond n కి మీనింగ్ ఏంటి? This is the meaning. Okay, n is smaller than epsilon. So n oka ikkada undi anukundam. Let us consider n is somewhere here. Okay, and epsilon is somewhere here. Pon oka axis esukundam, confuse avakunda. Let's consider a straight line where we have epsilon here, 0 here, and n somewhere here. And for every m comma n which is greater than n, for every m comma small n which is greater than n, ante ikkada unna random mn which is greater than n కన్నా ఎక్కువ ఉండాలి. ఎప్సిలాన్ కన్నా ఎక్కువ తక్కువ సంబంధం లేదు, n కన్నా ఎక్కువ ఉండాలి mn వాల్యూస్. ఓకే, ఇఫ్ ఐ డూ m మైనస్ n మ్యాగ్ అంటే m మైనస్ n n మైనస్ m ఏం చేసినా కూడా దిస్ వాల్యూ షుడ్ బి లోవర్ దాన్ ఎప్సిలాన్. ఓకే, ఇఫ్ దిస్ ఇస్ సాటిస్ఫైడ్ ఫర్ ఆల్ mn greater than n, then I will say that my Cauchy sequence is converged అని అంటాను నేను. Got it? Straightforward stuff. There's nothing deep here, or there's nothing, confused or whatever. Just take a value epsilon greater than 0. ఏదో ఒక వాల్యూ తీసుకోండి. Else I will just take any value. So epsilon greater than 0, let us consider epsilon as 5, n as 2. So m comma n can be what are the possible combinations it can be? 3 4 4 3 ఉండొచ్చు అనుకుందాం. Okay, because what did I say? For all m comma n greater than n. So 4 3 ఉండొచ్చు, and it can be so on. Can be so on up to positive infinity. Okay, now ఈ so on up to positive infinity కాకుండా నేను ఒక 8 3 దాకే తీసుకున్నా అనుకుందాం. పోనీ 8 4 దాకే తీసుకున్నా. Okay, let us consider these three are the actual values. 3 4 4 3 4 8 ఇంతే ఉన్న వాల్యూస్ నా దగ్గర అనుకుందాం. Now do the stuff. So what is the stuff? xm minus xn magnitude. So first 3 minus 4 ఎంత వస్తుంది? -1. mag 1 ఏం so greater than 5. True. Now 4 3 same 1 greater than 5. True. Now 4 8 4 minus 8 I am getting -4 mag 4 greater than 5. True. So what is 5? Epsilon value. Okay, so every xm minus xn mag in the sense nothing but a modulus value, this is satisfied. Yes or no? For the values which I took here, for every m and n value, when I'm taking a Cauchy values, this particular thing is getting satisfied. Yes or no? ఎందుకంటే this is 1 greater than 5. When I try this one, ఇది ట్రై చేసినప్పుడు ఇది వచ్చింది. 4,3 ట్రై చేసినప్పుడు ఇది వచ్చింది. And when I'm trying 4,8, I got this. Okay, so for every m and n value, this thing is satisfied, right? Now I can confidently say like my Cauchy sequence is converged అని అంట. Got it? Understood everyone what is a Cauchy sequence? Simply to put, simple example is this one. Very straightforward. M, n, capital N, epsilon. Just 4 variables. Find the values. End of discussion. Okay. Now, if a Cauchy is converged within the limits, ఒక particular limits లోపలే నా Cauchy అనేది converge అయింది అనుకుందాం, then I will say it is complete in nature. Okay. When a Cauchy is converged within a particular limit, for example, as I said, this m and n values, this can extend up to infinity. Yes or no? ఎందుకు? Is greater than n. I am not having any ending criteria. I have only the starting limit. కానీ ending limit నాకు ఉందా? ఇక్కడ n 10 అనుకుందాం. Let us consider capital N equal to 10. My m and small n can be infinite as well, right? It is greater than 10. Okay, so that's where it comes. When a Cauchy is converged within a limit, ఒక limit లోపల converge అయిపోయింది అనుకుందాం, then I will say it is complete in nature. Understood? Everyone? Got it? So simply to put, a Cauchy should be converged in nature. Anta అయిపోయింది. So then I will say it is complete in nature. Okay. Now, inner product. So what is an inner product ante? It is nothing but a complicated version of your dot product. That is known as inner product. So let us go with the dot product first. Vector A. ఎలా తీసుకుందాం? So a1x plus a2y plus a3c plus so on up to am some random variable zm అనుకుందాం. Okay. This is vector A. Consider vector B the same way. What is A dot B? Dot product. What is A dot B? A dot B gives me what? A1 into B1 plus A2 B2 plus so on up to AM BM. So this is known as dot product. Okay. This is simply known as dot product. దీన్ని నేను ఏమంటాను? Dot product అంటాను. Okay, I will call it as a dot product. Okay. Simple dot product looks like this. What is an inner product? అసలు inner product అంటే ఏంటి? నా దగ్గర dot product ఉంది. Cool. So what exactly is an inner product? So inner product is defined something like this. ఇలా డిఫైన్ చేస్తాం అన్నమాట. So this is known as inner product. Okay, we'll call it as an inner product. Now, this is nothing but a dot product, but for complex conjugates also. Okay, a dot product for your complex numbers as well or conjugates as well. So that's where we will call it as a inner product. So meaning for the same vectors, when I take the inner product, it looks something like this. It looks like so this is how it looks like. So what is this star signifies? For example, let us consider A equal to 2 plus 3i. A star is 2 minus 3i. Okay. So that is the deal anamata. If A is 2, A star is what? Come on. If A is 2, A star will be 2 only. Okay. This star guys then he will shift only the imaginary terms sign. Okay. This star only works if you're having an imaginary term. Imaginary term unte dani yoka sign ni flip cheస్తారు అన్నమాట. ఓకేనా? It will not change the values of your real value. Real value యొక్క sign flip చెయ్యదు. It only flips the sign of your imaginary value. Got it? So this is a star and this is the complex thing. So I'll represent A star is nothing but A dagger అని కూడా అనొచ్చు. Okay? Not T, dagger. This is T. This is dagger. Okay? So దీని dagger అని అంటాం. సరేనా? So that is this one. So I can represent it like star. I can represent it like dagger as well. Sarana? That is a simple deal behind it. So this is known as my inner product. And inner product always gives me something known as complex scalar. Just keep that in your mind. So inner product's output is always a complex scalar. Sarana? That's the basic thing which you need to remember. And inner product is the starting of your quantum mechanics. Quantum mechanics నేను చేయాలనుకుంటే ఫస్ట్ చేయాల్సింది inner product నే. Okay, inner product is nothing but a complex scalar. Done? Understood? Now. Okay, so we have 5 more minutes. So after that, I will just conclude the session. Now, so yeah, it's better. It's enough up to here for today. So if you're having any sort of queries, you can ask me right now, actually. లైక్ నాకు ఈ డౌట్ ఉందమ్మా అని అంటే అడగొచ్చు, ప్రాబ్లం ఏం లేదు. సో యూ హ్యావ్ మైక్స్, మోర్ దాన్ వన్ మైక్ we have, I guess, I don't know. So if you're having any sort of queries, you can ask me right now. Such a smart people, 0% doubts.
See, sir, up to what extent you have covered on that, they don't have any doubts actually. So that's
Okay,
where they are silent.
completely all right, understandable. Okay, so yeah, I think I'll simply conclude the session of today. So thank you so much for to- bearing this torture.
It's really such a remarkable session, sir. Thank you so much. And before concluding, I'd like to request any students if you are ready to summarize this session, or else let me summarize this session. So today's lecture, the very first one of our Qiskit Fall Fest 2025 workshop series, was truly a perfect blend of clarity, curiosity, and insights. So our esteemed resource person, Dr.Jnan Yalla, took us on an enlightening journey to the fascinating world of quantum computing, and starting right from the very basics, truly from the scratch, making sure every student, each one of us, could follow along comfortably. He began by building the foundations, explaining what a computer is, how it works from input to output, and the underlying principles that make it possible. And we also explored the core subjects that drive this process: Boolean algebra and physics, the two powerful pillars that describe how computers process and generate output. And he also beautifully connected everyday physics with computing, from how a mobile touchscreen detects electric pulses to how Boolean values represent binary truths, the zeros and ones. These deterministic values, he explained, are what makes logical decisions possible inside a computer. And moving forward, he bridged this understanding with classical physics, touching upon Newtonian and Einsteinian principles, and then introduced us to the most intriguing realm, quantum physics. We learned that while classical physics governs the macroscopic world, quantum physics deals with the microscopic, the subatomic world where the usual laws no longer apply. And Dr. Gnan explained how particles at this level can behave like waves, exist in multiple states at once through the concept of superposition, and form the backbone of quantum computing, a field that doesn't rely on bits and alone, but on qubits, which can represent 0, 1, or both simultaneously. And through this, we understood how quantum computers can perform computations at speeds unimaginable to classical systems. And through simple yet powerful analogies and clear explanations, Sir really made us realize that quantum computing isn't just a topic of the future, it's the bridge between science and possibility, redefining how we understand information and computation. We are also got introduced to the Hilbert spaces, the abstract home where all quantum states live. It's not physical, but mathematical, an infinite dimensional space that makes quantum mechanics both powerful and a little dizzying. And then came the classic Schrodinger cat experiment, the cat that's both alive and dead until observed. So, a playful paradox that perfectly explains how quantum particles exist in multiple states at once, mysterious, yet surprisingly logical in its own way. Finally, we have touched upon the Cauchy sequence, where elements keep getting closer until they converge within limits. Just like how our every new concept today brought us closer to truly understanding quantum mechanics. This session was really enriching. It's not just informative but deeply inspiring, sir. It's a perfect introduction for beginners like us into a domain that's shaping the next generation of technology. And we are really grateful for such an inspiring and knowledgeful session, sir. Thank you so much. On behalf of the entire university, Archivkati Srikakulam, and the Qiskit Fall Fest organizing team, I would like to extend my heartfelt gratitude to our resource person, Dr.Jnan Yalla sir, for his valuable time, his patience, and his wonderful way of simplifying such complex concepts into easily understandable insights. Sir, your session has truly sparked curiosity and confidence in all our students to explore the world of quantum computing further. I believe most of the students and even more will turn up tomorrow to attend your workshop and learn even more. So I also like to express our sincere thanks to our faculty members and administration for your active engagement, for your constant support and encouragement in making this workshop possible. And of course, a very huge thank you to all the participants for your active engagement and the enthusiasm throughout the entire session today. I hope all of you will turn up tomorrow also. So your energy truly made this workshop interactive and memorable. Let's carry forward this learning spirit as we continue to explore the field and the fascinating world of Qiskit and quantum computing in the upcoming sessions. Thank you all for your patience and time, and let's wind up this session. Thank you so much, everybody. And a little announcement, everyone. There will be a QR displaying on the screen in front of you. I request all the participants and all the attendees to scan that QR code and give your valuable feedback, and this will also be considered as your attendance submission. So to confirm your attendance as well as to give the feedback of our first workshop session, please scan the QR. Only after filling the feedback form you may leave. In the meanwhile, I also wanted to let you know that the hackathon registrations closes soon. So if any one of you are interested or your friends who might have been interested, just let them know the information. And if you are interested, kindly register at an earliest. Hope you all have scanned the Google form for the attendance and the feedback. These are all our social media pages, the QR codes which have been displayed after the feedback form. Follow them to keep you posted. Let us keep you posted about all the updates of Qiskit Fall Fest for all this week long. Thank you, everyone.
Wanted to create quantum valley in India, that is where Andhra Pradesh